I'm just going to kill time for a little bit to let more people come in. But so 3 things. Firstly, it's really nice to see a bunch of people who I've met in the field. Some of you I've gone birding with. I have to say it's kind of weird seeing you all in nice non-field clothes. Bruce, where did you get that shirt? It's amazing. Thank you. Can I have, okay, we'll talk later. Secondly, thanks to everyone who's wearing a mask. I founded and lead a set of birding outings for people with long COVID and other similar chronic illnesses, which I guarantee you do not want. So thank you to everyone who's doing something small to protect our entire community tonight. And then the third thing is thank you to this community for welcoming me so warmly. As Glenn said, I moved to the Bay Area last May and started birding kind of last September. And this has been a very wonderful place to kick that off. And everyone has been really lovely. So thank you for that. Tonight, I'm going to talk about how all the birds that you love and see and spend time with experience the world. This is a talk based on my second book, An Immense World, how animal senses reveal the hidden realms around us. If any of you have a copy of the book, I'm happy to sign later. If not, you can get your copy from bookshop.org, and I'm sure I will bump into you in a future GGBA event. All right, I'm going to start off with some poetry. So in 1790, can we maximize this screen? Yeah, can everyone hear me? Oh, okay. Yeah, you want It might actually be that you can't do that because it's on Zoom, in which case it doesn't matter. All right. Okay, we'll start with some poetry. So in 1790, as part of the marriage of heaven and hell, William Blake wrote this stanza. How do you know but every bird that cuts the airy way is an immense world of delight closed by our senses 5. I love this verse, but it also speaks to the big theme of the book, which is that animals are spectacular in ways that we sometimes miss because of the limitations of our own senses, because we, despite all of our technology and our vaunted intelligence, are only capable of perceiving a thin sliver of the fullness of reality. And that gives us only a partial understanding of the lives of other creatures, even those who we spend an inordinate amount of time obsessing over. For example, now the field marks are very subtle here, but this is a dog. And specifically, this is my dog. His name is Typo. People tend to notice his very cute ears and his very cute eyes, but I want you instead to focus on his nose, which is the seat of his most important sense. Smell is the main way through which Typo interacts with the world and experiences the world. He will smell things on our walks that I cannot sense. All dog owners here will be familiar with the experience of walking your dog along and having it grind to a halt and furiously investigate a patch of pavement that looks completely nondescript to your eyes. Typo also sees different colors than what I see. He hears different frequencies than what I hear. He exists in a world dominated by other stimuli that I don't perceive, so that even when we are sharing the same physical space, standing right next to each other, we're experiencing that space in radically different ways. We each exist in our own sensory bubble. And there is a wonderful word for those bubbles. That word is no. All right. That word is Umwelt, not Never give anyone else your slides. The word is Umwelt. It is just German for environment, but it means more than just the physical environment. My Umwelt is not this microphone, it is not this podium, it's not this floor beneath me. My Umwelt is my sensory environment. It is this unique cocktail of sights and sounds and textures and smells that I am privy to. and that another animal or even another individual might not be. I think that this is actually one of the most profound and beautiful concepts in all of biology, because it is a very humbling idea. It shows us that despite the fact that our perception of the world feels complete, it is not. It is only partial. It is limited. And for that same reason, the Umwelt concept is wonderfully expansive. It tells us that everywhere we are, even in the most mundane of settings, there is magic to be found. There is the extraordinary always lurking behind the ordinary. And one way to experience that extraordinary hidden side of the world is to think about what other animals are experiencing. By extending our curiosity and our empathy to them, we can go on incredible journeys without having to travel anywhere. So I'm going to take you on a tour tonight through the Umwelten of the birds that you love, to experience the world through their senses, and to show how much you're missing through your eyes, your ears, and your other sense organs. And we're going to start with vision, which is the sense that most of us rely on the most, and a sense that is also incredibly important to birds too. Birds, like us, have two eyes. They're on their heads. Neither of these traits is a given around the animal kingdom. There are lots of very weird eye setups out there, but birds are similar to us. They are different in that, with a few exceptions, like owls, their eyes tend to be on the sides of their heads. A very simple difference that actually radically changed their experience of the visual worlds. A scientist named Graham Martin said it best when he said that the human visual world is in front and humans move into it. But the avian world is around and birds move through it. They can see to the side of their heads without needing to turn around. Many species can even see behind them. So when we use this phrase, a bird's eye view, to basically mean anything that is our normal view but a bit elevated, we are using it misleadingly. A bird's eye view is not just a higher version of one. It is more immersive, more surrounding. Many birds have eyes not just on the sides of their heads, but a little bit further up too. A lot of ducks have this setup. This is a mottled duck. That setup means that when this duck is sitting on the surface of a lake, it can see the entirety of the sky above its head without needing to look around. Herons have eyes that face downwards a little bit, so that when a heron is standing straight with its beak facing forwards, it can see the fish swimming between its feet. Its visual field covers 180 degrees in the vertical. It covers an extraordinary amount of space. For those of you who've seen American bitterns at Coyote Hills, when the bitterns are doing their sky pointing thing, that same coverage means that they too can see the entirety of the sky without needing to look around. These visual fields can have strange consequences. So this is a griffon vulture, and this is what its visual field looks like. It extends quite a long way through the sides, so a vulture soaring can see other vultures soaring in the sky around it without needing to look around. But you might notice that vertically, that visual field is quite narrow. It's certainly not the 180 coverage that a heron gets. There are these blind spots above and below. And when the vulture flies, its head tends to point downwards a little bit to look for prey, which means that the blind spot is now directly in front of the bird. And this is thought to be one reason why vultures and other raptors often collide into really obvious things like wind turbines, which you would have thought, given their incredibly good vision, they would easily avoid. But they can't avoid it if they can't see it, and they can't see it if it's not in their field of view. And for millions of years of their evolutionary history, they never needed to see anything directly in front of them as they were soaring high up in the sky. I said that birds of prey have very good, very high, very acute vision. And actually, they are one of our only rivals in that department. Humans tend to have very, very high resolution vision, higher than most other animals. I mean, I am wearing -6 and -7.5 contact lenses, so maybe not me per se, but like in general, as a species, we see a lot more detail than what most other animals are seeing. Actually, about half of birds are legally blind by human standards. But raptors, like this wedge-tailed eagle from Australia, have very, very, very sharp eyesight. So this bird is actually the current record holder for resolution of vision. I want you all to give me a thumbs up. Great. I'm actually going to use this to explain something. This isn't just for self-validation, but this feels good. I'm liking this. So if you do this, if you imagine a pair of black and white lines painted on your thumbnail, you would easily be able to tell them apart. Now, if you had 60 pairs of black and white lines, it might not seem like it, but you would actually still be able to resolve that. That's pretty much at the limit of the resolution of our vision. This eagle can do about 140 pairs. So it is seeing the world on a screen with about twice as many pixels as ours and can spot a rat from about a mile away. It does this in part because its retina, like yours, is full of light-sensitive cells, photoreceptors, but its photoreceptors are incredibly svelte and narrow, so it packs a lot of them in the same area. It's why it has more pixels on its mental screen. There is one huge drawback to that, which is that when light levels get low, you are now splitting the total amount of very little light among a higher number of receptors, which then don't work. This means that eagles struggle like we do when the light gets low. That's why there are no nocturnal eagles. This is a trade-off that all animals at sea face. You can either have an eye that is very, very high resolution, or you can have an eye that is very sensitive, and you can never have both at the same time. Some birds also have vision that is much faster than ours. This is a pied flycatcher. This is the fastest vision of any vertebrate. So one way of thinking about the speed of vision is to imagine a flickering light. If that light was flickering maybe once or twice a second, you would definitely see it. It would probably be quite annoying. But once it gets to about 60 times a second, the flickers just look continuous to us. It's why like fluorescent lights that do flicker often look like they're just giving a steady glow. That you can sort of think about that as like the frame rate of human vision, right? So it's 60 times per second. This flycatcher, it's about 146. So it is capable of resolving much faster movements than we can resolve, which is a good thing because it eats fast-flying insects and needs to be able to track their movements. I think a lot of insect-eating birds have similarly fast movement. Incidentally, for this reason, a lot of birds probably find fluorescent lights very, very irritating. They tend to flicker at about 100 times per second, which we cannot detect, but a lot of them can. Many birds are also famously incredibly colorful. I went to Kenya recently. This is a lilac-breasted roller, which is an accurate name, but it's also really like the lilac-breasted, white-browed, cyan-crowned, olive-backed, blue-winged roller. It really seems weird to pick up the lilac breast, but like, fine. While we might gawp at these colors, and quite rightly so, we should understand that this is just a thin shadow of what the birds themselves are seeing. You can imagine like an even more kaleidoscopic experience of this bird than what your eyes are giving you. Bird visual palettes are much richer than ours for at least two reasons. First, most of them can see ultraviolet, a color just off the violet end of the rainbow that we typically cannot detect. If you can see UV, a lot of the natural world looks very, very different. So here is a black-eyed Susan. There's a flower that to us on the left looks just plain yellow. But to an eye that can see UV has this very vivid bullseye, this halo in the middle. Many, many flowers have these patterns. Sunflowers have patterns like this. They include halos and bullseyes and landing strips and arrows that direct the attention of pollinating insects, many of which can see UV. And since birds can see UV too, they are also clued in into this hidden language that flowers have. But flowers are not the only thing that have striking UV patterns. Bird feathers also do. This is a blue tit, very common bird in the UK, where I'm from. The blue parts of this bird actually reflect quite a lot of ultraviolet. This was discovered in 1998 by two independent researchers, one of whom published one of my favorite research paper titles ever, Blue Tits Are Ultraviolet Tits. But also, there's a difference between the sexes. So male and female blue tits look very much the same to our eyes, but they look very different to each other because the males reflect a lot of UV on those blue markings. So to us, they are sexually monochromatic, look the same. To them, they are sexually dichromatic. Males and females look different. And actually, that turns out to be true for a lot, actually most of the passerines, the songbirds. So it used to be thought that about 67%, but 2 in 3 passerine species were sexually monochromatic, males and females look the same. But a study from 2005 showed that that's only actually true for about 1/5 to 1/4 of them. Under UV, there are very, very clear differences in species that really look the same to us. So a male robin's breast blazes with UV. This is the yellow-breasted chat that was at Lake Elizabeth earlier this year. You can see this very, what looks like a uniform yellow marking from the throat all the way to the belly. Under UV, there's actually a kind of a demarcation midway through that. So another pattern that's obvious to the birds themselves and not to us. Some of you might have heard the thing about kestrels and UV. No? Well, I'm going to tell you about it now. There is an idea that kestrels can track voles because vole urine reflects a lot of UV. This idea shows up a lot in books, in documentaries, and it is a myth. The kestrels absolutely cannot see that because vole urine does not reflect UV and is not distinguishable from water. I don't know where people got that from. It is not true. Now, I said that bird color vision differs from ours in 2 important ways. One is UV. For the other, let's return to typo for a second, just to remind you, not a bird. This image shows how I see Typo and his favorite toys. And this image shows what Typo would see in that same situation. So it is a common myth that dogs don't see color, they only see black and white. It's not true, they do see color, but clearly a much more limited palette than we do. So reds will look like this kind of muddy, mustardy yellow. Violets will look like a kind of dark blue. Greens will look kind of in the middle. It's really about blues and yellows, whites and blacks and grays. This is because the average human eye has 3 kinds of cone cells, which are responsible for color discrimination. So think of them as 3 kinds of color sensing cells. Dogs have 2. So we are trichromatic, they are dichromatic. And as a consequence, they probably see about 1% of the colors we can see. So we see 100 times more different hues than what our pets. The same is also true for cats, for horses, for a lot of other mammals. It's also true for a lot of people with red-green color blindness. So if any of you have that, these 2 images probably look very much the same. So I point this out because it helps to think about this difference when I tell you that birds have 4 kinds of cones. They are tetrachromats. And that doesn't just mean that their visual palette is extended at the margins. It's not just they see our rainbow plus UV. It really means that they have unlocked an entire dimension of colors that is inaccessible to us. So Cassie Stoddard did some great work with broad-tailed hummingbirds where she trained them to visit certain feeders and showed that they could very easily tell apart feeders that had green lights on them versus, say, green plus ultraviolet, that look completely identical to us, but were easily discernible to the hummingbirds themselves. And hummingbirds and really all other birds are probably seeing 100 times more colors than we are seeing, just as I can see 100 times more colors than my dogs can see. And you will note that I have not shown you a visual reconstruction of what that's like, because that is impossible. I cannot take a tetrachromatic view of the world and put it in and show it in a way that a trichromatic eye can pass. You really have to use your imagination, and I think that this taxes the limits of mine. This is actually a common problem with thinking about the Umwelt concept. Thomas Nagel wrote about this in his essay, What Is It Like to Be a Bat?, where he argued that you could imagine flying through the air on leathery wings and with eating insects, but you would never really understand what it is like to echolocate, to perceive the world through sonar in the way a bat can. Similarly, I think that for birds, I can tell you that a mallard has a wraparound vision of the entire sky. I can tell you that a hummingbird sees a dimension of colors that we can't see. I can tell you that a pied flycatcher sees twice the frame rate of our vision. But it's really, really hard to actually grasp what that means for the bird. And in some ways, we will never know. And part of the point of my book is that despite the futility of the task, it's worth attempting, because it teaches us something important about the lives of other creatures, and it reveals something new about the world that we live in. I've dwelled on vision quite a lot because it is important to birds as it is to us, but it is just one of several senses that they use. It's not massively helpful when you're trying to find things that you can't see, that are hidden by darkness, or, for example, buried in mud. And so when these red knots and many other shorebirds forage by probing into mud, they're not using vision, they're using touch. Bird beaks are made of bone and keratin, the stuff your fingernails are made out of. They seem, I don't know what they seem like to you. They seem kind of inanimate, maybe insensitive to me. I think that's the sort of stereotype one has of them. But in many species, the tip of the bill, like in these red knots, contains a lot of mechanoreceptor cells, cells that are uniquely and exquisitely sensitive to changes in pressure, touch sensors. This kind of corncob structure at the tip of the red knot's bill shows that each of those little pits would be full of mechanoreceptors. So the bird pushes its beak down into the mud and feels very keenly what the beak encounters. But there is more to it than that. As the beak descends into the mud, it pushes down on the thin rivulets of water that lie between the sand grains, and it creates a pressure wave that radiates outwards. If there is a hard object in the way of that pressure wave, like, say, a clam or any kind of buried food, then the water has to flow around it, and that distorts the pattern of pressure. And that bill can detect those distortions, which means that when a red knot is foraging, it doesn't need to actually touch food to know that it's there. It can sense stuff that exists beyond, that lies beyond where the bill is actually probing. And for that reason, it's because of that they're really, really effective. So red knots tend to find food about 8 times more frequently than you would expect if they were just haphazardly probing into the mud. They use a kind of touch that works at a distance. We think of touch as a sense that requires direct contact, not always. Dabbling ducks like this northern shoveler are also masters of touch. Their bills are packed with mechanoreceptors, and in many places are as densely packed, those cells are as densely packed as they are on our fingertips, which are some of the most sensitive organs of touch in the animal kingdom. So again, you have this organ that doesn't scream sensitivity, but absolutely embodies that in practice. With these bills, dabbling ducks can grab fast-swimming tadpoles in the dark. They can filter edible morsels from inedible mud. Tim Burkhead, author of Bird Sense, wrote about this beautifully. He said, imagine being given a bowl of muesli and milk to which has been added a handful of fine gravel, and trying to sift the gravel out with your face. It's what these ducks are doing all the time. Many birds that don't specialize in touch still rely upon it in interesting ways. Peafowl have some of the most ostentatious feathers of any bird, and you know what they do. They fan the tail out, they'll vibrate, they'll shake the tail. They tend to shake the tail at a frequency of 26 hertz, so 26 times a second. What do you think is the resonant frequency of those feathers on the peacock's crest? It's 26 hertz. That is probably not a coincidence. It means that when a peahen is standing in front of a courting peacock, she likely doesn't just see the display, but feels it in her head. At the base of each of those crest feathers is a very small feather called a filoplume. That's just a single strand with a little tuft at the end. When the moving air shakes the crest feather then shakes the filoplume triggers a nervous signal that goes to the brain. But filoplumes are everywhere, right? They're not just on a peacock's crest, they're at the base of a lot of other bird feathers. Birds probably use them to monitor the position of their feathers. They can tell when plumage is ruffled or needs a preen. And it's possible that filoplumes really, really play an important role when the birds are flying. So maybe these tactile sensors allow a bird to tell when it is hitting a position of terrible lift, when it's about to stall, and correct for that. This is a black skimmer that I photographed in Hayward, showing that precise flying very beautifully. French ophthalmologist André Rochon-Duvigneau once wrote that a bird is a wing guided by an eye. I think he was wrong. The wings also guide themselves through touch. I picked the skimmer for this because it's also a master of touch. So the lower mandible is much larger than the upper one. The bird flies over the surface of the water and drags the lower mandible through the water. When it hits anything, the mouth closes, the bird gets a meal, or in the case of this particular individual, a stick. This is a skill unique to the skimmers, and it means that they can forage nocturnally. I think one birder in the Bay Area posted some really nice photos from the ferry taken at night of skimmers skimming along the side. Other nocturnal birds rely on a very different sense, hearing. The last speaker in the series was Jennifer Ackerman, who just wrote a fantastic book about owls and what they're like. So I'm not going to dwell too much on this. I do want to point out, though, that it wasn't actually too long ago that most people thought that owls only really used vision, like very large eyes, to hunt in the darkness. And some definitely do. So screech owls tend to prioritize vision. But in 1956, Roger Payne, who was also the guy who told us about whale song, showed that barn owls rely on exceptional hearing. So Payne worked with an owl called Wall, after the owl from Winnie the Pooh. He put Wall in a garage where he had blacked open the windows and strewn the floor with dried leaves, and then he would release mice onto that floor. And even though there was no light, the owl would snatch the mice with total accuracy. If Payne took wads of paper and dragged them through the floor, the owl would also attack. If he tied a leaf to the tail of a mouse, so that the rustling was now coming from behind it, the owl would miss its attacks. So relies on hearing. Many structures on its face are important for that sense. This whole radar dish setup consists of very stiff feathers which funnel incoming sound towards the owl's ears, which are roughly behind its eyes. Those ears are asymmetric. So if the owl's face is a clock, then the ears are at 2 o'clock and 8 o'clock. And that setup means that owls are very good at localizing where sound is coming from, not only in the horizontal, but in the vertical. So I can tell, I can theoretically tell where sounds are coming from, because if they're coming from over here, they'll hit this ear before that ear, and there'll be a slight volume difference too. But if they're coming from 6 feet above me versus 6 feet below, they arrive in my ears at the same time, and I don't know where they're coming from. Owls are really, really good at that. I say theoretically because birding has taught me that I'm really, really bad at localizing sound. I don't know if any of you have had this humiliating experience of like hearing a bird call and being like, no, it's literally 180 degrees in the other direction. With these adaptations, and generally just like an auditory setup that is like more, the cochlea, the structure in the inner ear, more, the auditory processing centers in the brain, more. This bird is tuned for hearing. Because of that, barn owls can detect faint noises that we would never detect. But even in the sounds that we do hear, we are missing quite a lot. Which bird is this? This is a spectrogram of a recording I made. It is in the Bay Area. Anyone take a guess? Come on. It's in the Bay Area. There's a million birds in the Bay Area. Okay, this is a Pacific wren. This is a Pacific wren. This is one of, I don't really have a spark bird, but if I had a few, this would be on one of them. Look at everything that is going on here, right? These very quick changes in pitch and volume, all of this stuff, this complexity. How many of you have listened to a singing bird and heard something that you thought, and that made you think, I just can't hear everything that's going on there. There must be stuff that I am missing and that the birds themselves are picking up. Well, you're right to think. The frequency range of bird hearing is actually very similar to ours. So theoretically, we should be able to hear roughly all the notes they're singing, but you just can't keep up with the speed. The processing speed of bird hearing is much faster than ours. A guy called Masakazu Konishi showed this in the 1960s by recording from neurons in the hearing centers of a sparrow's brain and then playing rapid clicks to it. So click, the neurons fire, click, they fire. 770 clicks per second, and the neurons are still keeping time. At that speed, with little clicks being played just barely more than a millisecond apart, a cat's neurons can only keep up 10% of the time, and the birds were just perfect. So they can process very fast changes in their songs, in their auditory world, than what we can process. This sense that there's more in the song than what you can hear, that is very real. And a guy called Robert Dooling showed this in great experiments with this bird. This is the zebra finch from Northern Australia. He would present them with pairs of buzzy sounds, and he trained them to indicate if they could tell the difference between those sounds. The pairs were typically identical, but Dooling would flip a tiny fragment in the middle. So imagine like taking a movie, taking like 3 frames in the middle of that and just reversing the order. Now, human ears could tell that that had happened if the amount of flipped noise was about 4 milliseconds. These birds weren't even phased by like 1 millisecond. They could always tell when something was weird. And then Dooling did some really, really cool experiments that I truly love. So the zebra finch songs consist of several syllables that they produce in a very, very fixed and repeated orders, like A, B, C, D, E. So the experimenters would take like one of those and flip them around and asked if the birds could tell the difference. Now, human listeners could not, even with practice, and the birds always could. So interesting, right? They are paying attention to subtle differences in the songs that we can't hear. Now then, he doubled the gap between 2 of the syllables. And now human listeners absolutely can tell the difference. It just sounds like a glitch in the recording. And the birds could not. Or at least they didn't care. One of the 2. Then he just flipped the order of the syllables completely. And now it sounds very, very distinct to us. And the birds, again, seemed to not be bothered or couldn't tell. So the finches are clearly caring about aspects of their songs that are very different from what we pick up. Like we care about the order of the notes. That's how we think about birds. That's how we transliterate bird songs into mnemonics that we can remember. And the finches just didn't care, right? What they care about are the tiny changes within the span of a single note. Those changes in volume and pitch that are called the temporal fine structure. When these birds sing, it really sounds like every individual is just singing the same thing again and again and again. But maybe it's those differences in the temporal fine structure that we can't perceive that allows them to encode meaning in a song. Maybe that's how they communicate specifics to each other. Another weird thing about bird hearing is that it changes over the seasons. So remember with vision, I told you that there was a trade-off between resolution and sensitivity. So you can either have an eye that's very, very sharp or an eye that works really well in the dark. There is a similar trade-off with hearing. So you can either have an ear that has very good temporal sensitivity, so it's very sensitive to those changes in pitch and volume that I showed you, or an ear that is very, very good with pitch. And those two qualities seesaw against each other. And sometimes with certain birds, they seesaw against each other in different ways over the course of a year. So this is a Carolina chickadee. It does this chickadee call with rapid pitch and volume changes. In the fall, when this bird is very sociable, it needs to pass all the information that's encoded within that temporal fine structure, and its ear tends to be more, it tends to have a much higher temporal resolution at the cost of sensitivity to pitch. But in spring, the song changes. It starts doing this courtship song that's phoebe, phoebe, so 4 notes, each of which is close to a pure tone. A male's sexiness depends on the consistency with which he can sing those notes and in getting exactly the right pitch drop between the phi and the b. Now, pitch is all important, and the ears actually change so that they become more attuned to pitch at the cost of temporal resolution. So speed takes all in the fall, pitch is king in the spring. The white-breasted nuthatch does something different. Its courtship song, that kind of nasal wah, 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 has a temporal fine structure that includes very fast changes in volume. So in the spring, its hearing becomes faster, higher temporal resolution than in the breeding season and less sensitive to pitch. Ears can either have high temporal resolution or pitch sensitivity. If you're a bird, you can just get the best of both worlds, depending on your needs. Finally, on hearing, this bird uses its ears in a very special way. Does anyone know what this is? Great, it's so good. This is an oil bird. It lives in caves in South America. As it enters and exits those caves, it makes clicking noises. These clicks are a form of echolocation. They're the same skill that bats and dolphins use. So a bat will make high-pitched calls as it flies and listen out for the echoes bouncing off objects in the air around it. By timing very precisely how long the call takes to go away from the bat and to return to its ears, it can judge its distance to other objects. This is a form of sonar and allows bats to avoid large obstacles, to grab insects out of midair, to pluck spiders from their webs. Oil birds seem to use a very, very rudimentary version of this. And they have this there's not a lot that's known about their echolocation, and what is known is very puzzling. So with bats, there's a very close match between the frequency of the bat's call and the pitches that its ear are most sensitive to, right? So emitter and receiver are very closely aligned. That's not the case with oil birds. Their hearing is best at around 2 kilohertz. The clicks have frequencies mostly between 7 and 23 kilohertz. So some parts of the clicks, the bird probably can't actually hear. Why this is the case is a bit of a mystery, but maybe it's just that birds have been latecomers on the echolocation scene. Maybe if we give oil birds a few tens of millions of years, they're going to be as fine-tuned as bats currently are. I think echolocation is interesting, though, because when the first scientists who suggested that this might be how bats move through the world in the 1940s were kind of ridiculed for this. It just seemed preposterous, like bats see with their ears, come on. And there's a lot in sensory biology that works like that, where dogma eventually gets overturned by people who discover animals using their senses in ways that just seemed unbelievable at the time. For example, Donald Griffin, one of the pioneers of bat echolocation, himself was incredibly skeptical about the idea that animals could sense the magnetic field of the Earth itself, because that field contains very, very, very little energy, much, much, much less energy than, say, a photon of light from the sun. It just seemed preposterous that animals would be able to detect that. And yet it turns out that birds absolutely can. And a lot of birds can. There was a really good paper on magnetoreception this year, which featured, I think, brown pelicans, Swainson's hawks, a lot of really cool birds that we have around us that are very different from the small songbirds like this Eurasian robin that were the first subjects of magnetoreception research. So in the 1950s, some German scientists realized that if you took robins and put them in a darkened room devoid of any other landmarks, they will still hop in the right direction when it comes time to migrate. They measured this in a lot of fun ways, including eventually just putting ink pads at the bottom of the cages and then filter paper around the edges and just counting where the footprints were going as the birds tried to hop in the direction that they knew in their heads that they needed to head in. As I said, the Earth's magnetic field is extremely weak. So the random jiggling motions that molecules make when they just move around carry about 200 billion times more energy than the Earth's magnetic field. So it really is weird that animals can detect something so ludicrously faint. And indeed, magnetoreception, this magnetic sense, is still the only sense for which we don't have a sensor. So with vision, we know your eyes are what's responsible. I could go into inordinate detail about how the photoreceptors in your retina work. We have that all mapped out. We don't know that for magnetoreception. What is the organ? Which are the cells? How does any of that work? We do have good ideas, and there are three. One of them involves the inner ear. One involves the beak. But the one that has got the most traction involves the eye. And it also annoyingly involves a lot of quantum physics. So I am not going to try and explain it in any detail. But the general gist of it is that there are proteins in the bird's eye that are light sensitive. When light hits them, they switch shape and they enter a state when they can be influenced by the incredibly faint magnetic fields that surround the Earth. There's a lot of evidence behind this hypothesis. I don't think the people who have worked on that would say themselves that it is the case has been completely sealed, but there's a lot of momentum behind it. And I think if it is true, then it raises the really compelling possibility that birds can see the Earth's magnetic field. That maybe there's some kind of heads-up display in their vision that indicates the right direction for them to go in. Again, we don't know. We can only really imagine that. This is not the only sense that birds have that we didn't know about. You probably know this man. This is John James Audubon. He was a slave owner who dabbled in paint. In 1826, Audubon did some really terrible experiments with turkey vultures, which led him to claim that they find food with sight and not smell. His supporters did some even worse experiments and extended that claim to all birds. And for decades, the textbook wisdom was birds don't smell. Maybe some of you have heard that birds don't smell. I'm delighted to inform you that birds, in fact, do smell, and some of them smell very, very well. Two women corrected that myth. Betsy Bang was Bernice Wenzel was one of them. She was a physiologist who showed that the olfactory bulbs, it's a part of the brain that processes smell, of homing pigeons, turkey vultures, loads of other birds, would just light up when the birds were given whiffs of scented air to smell. Betsy Bang proved with anatomy what Wenzel did with physiology. She dissected the nasal passages of a lot of birds and very clearly showed a lot of anatomical apparatus dedicated to smell. She was the one who worked out what the tube noses of tube-nosed seabirds are for. Other people then took up that mantle. Gabrielle Nevitt showed what the tube noses are smelling for. Well, never copy captions between slides. That's humiliating. I'm the speaker. If I say it's an Anna's hummingbird, it absolutely is. No one's reviewing my this. I'm going to the bar. All right. So this is a black-browed albatross, not an Anna's hummingbird, as you correctly pointed out. As it flies over the ocean, that water looks featureless, but it is not. It is bursting with scent. One chemical that these albatrosses are particularly looking out for is called DMS, dimethyl sulfide. It is the scent of the sea. It smells kind of oystery and seaweedy, but in particular, it is the scent of bountiful seas. When plankton are munched on by krill and other organisms higher up in the food webs, they release DMS. And so this chemical gives the bird an indication of where rich sources of food are. As this bird flies over the water, it is not experiencing a flat and featureless landscape. It is experiencing rolling topography, mountains and valleys of scent that its nose can detect. DMS smellscapes are also tied to actual landscapes, so they are affected by the underwater topography, by seamounts and valleys that affect things like currents and nutrients that then affect the rise of DMS over the surface. And Nevitt believes that seabirds build a map of those locations over their lifespans, using their noses to learn where the best feeding spots, where their home nests. So birds can smell. What about taste? In 2004, the chicken became the first bird to have its genome sequenced. And looking at its DNA, scientists noticed something weird. The chicken was missing a gene that humans and other mammals require to taste sweet things, that builds a receptor for sugar. So chickens can't taste sweet stuff. But then they looked at the genomes of a lot of other birds and found the same thing, no sweet receptor gene. So maybe all birds can't taste sweet stuff. I think not, right? So yes, hummingbirds can taste sweet stuff, because Moore Baldwin discovered that they have actually tweaked a gene that builds a receptor for umami, so savory tastes, and have turned that into a sweet receptor. So they've re-evolved the ability to sense sugars that their ancestors, presumably dinosaurs, did not have. Now, it's pretty obvious why hummingbirds did that. But it turned out that passerines, so songbirds, the most common group of birds, also did basically the same thing independently. So they can also taste sweet stuff. Why did they do it? Well, one clue comes from Australia. This is a New Holland honeyeater, inventing a completely new form of flying. Australia has this unique combination of very nutrient-poor soils and a lot of sunlight. So its plants are very, very good at photosynthesizing, but very bad at turning all the sugars they produce into actual tissues. So what they don't use, they give away. So Australia's flowers are bursting with nectar. Australia's trees bleed sugar and gum from their barks. The whole continent is full of forests that are exuding calories. And that might be why the ancestors of songbirds, which, by the way, come from Australia, so like all the finches and the jays and the backyard birds that you have originated from this continent, that might be why songbirds came to re-evolve this sweet tooth and why Australian birds are so unusually large and aggressive and intelligent and vocal. They're just hopped up on sugar like all the time. But there's kind of an interesting story here that I think is not like really nailed down, but I find really compelling, right? So here you have the most successful group of birds in the world, and they come from an ancestor that re-evolved the sweet tooth in a place that was overflowing with calories. Like, was that part of the reason why they eventually became so successful? Like, you could sort of craft a story where this sensory ability allowed these birds to build up enough calories to then travel large distances to other parts of the world. It allowed them to find ready sources of calorific goodness wherever they landed. Maybe the story of bird song is also a story of sugar and a story of taste. Those changes, those events are really hard to nail down because they happened millions of years ago. But many changes are afoot in the sensory world of birds right now over the course of our lifetimes. Glenn talked a little bit about this in his slides in the annual meeting before this talk. But light pollution is a huge problem. We have bathed the darkness in light. 99% of Americans and Europeans now live under light polluted skies. And every year, the proportion of the planet covered by artificial light gets very slightly bigger, very slightly brighter. This is bad news for birds, especially on migration. In 1886, after Edison commercialized the electric light bulb, about 1,000 birds died after colliding with a single illuminated tower. And today, almost 7 million birds a year die in the US and Canada after flying into communication towers. A study done with the 9/11 tribute, two gleaming beams of light that shine into the New York sky, showed that at their peak, they would waylay about 1 million migratory birds every week. Sound pollution is a huge problem too. In the early 2000s, European researchers showed that in urban environments, a lot of birds are forced to shift the nature of their songs to cope. Great tits would sing at higher frequencies that were less easily masked by urban noise. Nightingales just belted out their tunes. But we now know that sound pollution has a lot of other negative effects on birds. One of the studies that I think best demonstrates this was published in 2012, where Jesse Barber and his colleagues built a phantom road in a ridge in Idaho that acted as an important stopover for migrating birds. So they just recorded the sound of a highway and then played it out of these speakers lashed to trees. So now you have only the sound of a road. You don't have the exhaust, you don't have the threat of being hit by a car, you only have the sound. And that was enough to reduce the species of birds in this area by 1/3, and to reduce the body weight of a lot of those that stayed behind because they kept on spending their time looking around for danger instead of doing the things that they needed to do, like foraging and putting on weight for their migration. These types of sensory pollution, I think, don't seem viscerally off-putting to us. They're very different to chemicals billowing from a smokestack or plastics befouling a beach. They don't create that same kind of visceral disgust, but they can be equally damaging to the animals that we care about. And I think that they can be detrimental to our own experience of those animals too. I've talked about sensory pollution as the pollution of disconnection, a type of pollution that severs our relationship with the natural world. Light pollution stops us from being able to see the stars in the night sky. Sound pollution stops us from being able to hear the birds that we want to hear. There is a reason why at the start of the pandemic, a lot of people talked about being able to suddenly hear birds for the first time. People joked about how humans were retreating back into their homes and the animals were rising up to take back the world that we had abandoned. But that wasn't true. It was just that when we were quieter, we heard more. And we not only heard more, but we heard over larger distances. Sound pollution collapses the radius of our own sensory bubble and thins out the noises that we can hear within it. I think when you put all these things together, it contributes to the sense of nature that is very prevalent in this country of being equivalent to stuff like this, right? So grand vistas, big remote national parks, your Yellowstones and Yosemites, your Grand Canyons. That's fine. Like, these are spectacular places. But I think if this is your idea of nature and wilderness, it means that it's always going to be distant from our daily lives, something remote, something inaccessible for most of us. And I think this community understands better than most that that's not true, that nature is here all the time. Oh, this is where the caption went. So I moved from DC to Oakland last May. And the first night I moved into my new house, we saw Anna's hummingbird perched on our tree. And as I was walking around, I became aware of so much more birdsong than what I was used to on the East Coast. Oak titmice and Bewick's wrens, the Pacific wrens and Redwood Regional. These are one of the reasons I took up birding last September. And since then, one thing I've loved most about birding here is its accessibility. Like, all of these photos were taken within about 30 or 40 minutes of my house, right? Seaplane Lagoon, Mission Peak, Elsie Roma, Belena Bay, Coyote Hills. These are sites that I go to all the time. They remind me that nature is all around us, there for us to savor. And to me, thinking about the Umwelt concept helps us to savor it more, to go on these grand adventures without needing to travel, to look at all these birds that we might see all the time, and to have a deeper appreciation of the possibilities of their existence. This is a gift, and I think it is a gift that might be uniquely human. I don't think that in this photo, my dog is wondering about what kinds of colors this crow might see. I don't think that this crow is thinking, what is this dog smelling that I am not? I can think about those things, and I can tell you about them. That ability to extend our curiosity and our empathy to know what other creatures are experiencing because of the products of science and technology, and just our minds asking the question, what is their world like, is something that is ours. And I think it is a gift that we should cherish. Thank you very much. Yes. Yeah. Thank you. Anyone have any questions?
Questions from the audience? I'll come around and.
Hi. First, I wanted to thank you for your writing during the pandemic. It was extraordinary, and I always looked forward to your stories. As a birder and also a chicken owner, I'm curious about whether birds can see in infrared. I have cameras in my yard for watching predators, etc., and I've often wondered if it bothers the chickens at night.
So not to my knowledge, but I don't know if that's because no one's looked or because it doesn't happen. But to my knowledge, no. I think that infrared sensing is actually quite a rare skill. Some animals have it. So a lot of parasites have it. It's a very good way of finding warm-blooded prey. So vampire bats can sense infrared. There are beetles that sense infrared because they lay their eggs in burn forests, so they head towards sources of fire. The only animals that might see infrared are rattlesnakes and other pit vipers. So they have two pits on the front of their faces that are really, really good infrared detectors. So they, if we turned off all the lights in this room and there was a rattlesnake on my head, I don't know why, it would be able to sense the body heat of a mouse on my finger. Whereas you all might struggle to like feel the heat of the person sitting next to you, right? So really, really incredible skill. We don't fully know how it works, but also those pits have nerves that eventually connect to those coming from the snake's eyes and end up in similar parts of the brain. So there are certainly scientists who study these animals who do suspect that maybe infrared is just another color to them, that they can see it in the way that we can see red to violet. But no, I don't know of any birds that might have that ability.
I also thank you for everything that you've done. So I on Tuesday I got to see the new film My Penguin Friend with the director Q&A over in San Francisco, and
Cool.
I've also years ago I helped raise baby Magellanic penguins at the San Francisco Zoo.
Right.
And they're one penguin species, unusually, that actually has a very long migration. And it's based on the true story of, I guess it was a juvenile penguin when it was first oiled. And this man in Brazil, which is the very, very northern end of their migration, rescued it. And then for 8 years, the penguin came back every year to visit him. And that would be a different sort of migration from the tube noses in that, penguins, obviously they can't fly, so they're going to be missing a lot of cues, presumably, that, the flying birds could get, but they're able to do a completely aquatic migration for thousands of miles from Argentina to, in this case, Brazil, and come back to the same house
Yeah.
every year. What sort of cue do you think they'd be using? Similar cues? Would the magnetic cues still work?
Yeah, that's a good question. So I don't know anything about penguin sensors in particular, but I could take a couple of guesses. Usually when I do these talks and Q&As, I have to tell people I can't explain why your pet does the weird thing that it does. And I feel like with this particular audience, I have to say, like, I can't explain why your favorite bird does the weird thing that it does. But so I think my best guesses, and if anyone actually is a penguin expert, please chip in, are smell still and magnetoreception. So smell, just because a lot of aquatic animals have very, very good senses of smell. So sharks famously, salmon famously. Being underwater certainly deprives you of that kind of aerial topography that a tube nose might pick up, but it's not going to render smell meaningless. Actually, quite the opposite. Smell travels over quite long distances underwater, and so that might be part of it. Certainly, the fact that magnetoreception has been discovered in a lot of very evolutionarily diverse birds suggests to me that it should be a skill that one thinks about when asking this kind of question for birds in general. And there are other aquatic long-distance migrants that likely use magnetoreception as well. There's a really cool study on whales showing that on days with intense solar storm activity, which tends to create magnetic anomalies in the Earth's field, some whales are more likely to strand. And I think there was actually another similar paper with birds that came out quite recently. But so all this to say, I think both of those are solid ideas, but how these animals are migrating over long distances under the water. So underwater, certainly we have precedent for that in other creatures.
So we're going to take a couple of questions from online. First, Devin asks, do male and female corvids have UV differences?
See previous answer, but I can't explain why that particular, right. So
most of them do, but
I don't know, but like, given that so the outcome of that paper was that around maybe 80% of passerines have those differences. So I would expect so.
Another question from Marilyn. How do red knots know the difference between clams and rocks?
Oh, that's a really good, I do not know the answer to that, but that's a great question. They don't. Great. All right. Yes, please. That would be amazing. Was this like Linus Posner's work? So he did a lot of the not touch experiments. Okay. Okay. Okay.
A great deal is known about the neurophysiology of binocular disparity tuning, particularly in mammals whose visual fields do not directly overlap. And of course, a number of the birds that you showed have such large visual fields that although their eyes are widely spaced, they do overlap. But there must be many that do not. And what is known about how the integration that's so important for flying raptors to target what's obviously necessary, namely clear tuning of the three-dimensional world.
So, stereopsis, that kind of binocular, what is commonly known as binocular vision, has actually only been shown like clearly for a few other animal species. And that's not to say that like other animals don't have this, but it's a very difficult thing to actually investigate. So it's been shown in, I think, praying mantises, cuttlefish. I don't know bird experiments, but to answer the question about raptors, yes, raptor eyes do tend to face a little bit more forward than those of most other birds, but it's not actually necessarily true that they are focusing with both eyes on their prey. So your eye has a zone right in the middle, that where your vision is most acute, that is the fovea. Birds have that too, these acute zones, but they tend to have, theirs tend to face to the sides, and raptors tend to have two in each eye, one that faces forward and one that faces a little bit off at about 45 degrees. And it's actually the 45-degree one that they use when hunting. So when a peregrine falcon stoops after a pigeon, it is not pointing its head straight down and focusing on it with two eyes. It is flying in a descending corkscrew so it can keep the pigeon in the 45-degree acute zone of one eye, and usually the right eye for reasons no one really understands.
I had a follow-up question about the infrared vision,
Yeah.
which is, I've wondered this for a long time and haven't really found a answer online, but I was wondering why infrared vision is so rare in the animal kingdom. I would sort of naively think that for any nocturnal predator, it would be really nice to be able to like see your prey glowing in the dark. And I don't know if that's because mammal doesn't actually emit enough infrared light for that to be useful. But your point about parasites made me wonder.
Yeah, so I think in part, so yes, kind of, right? So I think a part of this is about the amount of energy in the radiation. So UV at the opposite end of the spectrum is very energetic. It's why you get sunburns, right? Infrared is less so, so it's just harder to detect. And even so, the rattlesnakes that I talked about are a really instructive case here because yes, they may see infrared possibly, but that's going to be very, very blurry. So certainly no animal seems to have sharp infrared vision. So when you see like the videos from like thermal imaging cameras, like on nature documentaries, that's not what a rattlesnake sees. It's going to get something very, very blurry. Has anyone seen the movie Predator? Where it has the alien has thermal vision, but it's like kind of grainy. And this is the first time anyone's ever accused the movie Predator of being realistic. But that is actually what infrared vision is probably more going to be like. And maybe that explains why it's not more common.
Yeah, thank you for being here. I'm really curious about the sugar tasting.
Yeah.
So you named two families that taste sugar, the hummingbirds, passerines.
Yep.
As it turns out, those are two of at least the three families that I'm aware of that are known to learn their songs. Maybe
Mhm.
some other birds that learn their songs as well, but those are two. Most others, their songs are hardwired. And that could be a coincidence or maybe not. But
Right.
so the third one is parrots.
Mhm.
Can you say anything about the ability of parrots to taste sugar?
I cannot because I don't think that's been done yet. So this is actually very, very recent work. And I think I name checked Maud Baldwin, who as far as I know, is the only person who studies this particular thing. So the hummingbird work came out probably a decade or so ago. The songbird work only came out in 2022. So it is like new. It's hot off the presses, very, very new science. Parrots would be the obvious next thing to look at, I think. And I would be shocked if they did not also have the same kind of, it just seems like a very possible thing for birds to do.
We have another question online from Wing. Do raptors use sound to recognize their mate when they return to their nest location?
I don't know the answer to that. Does anyone else know the answer to that? Sorry. I am just a beginning bird, right? I couldn't even identify an albatross, right? Don't listen to anything I'm saying.
And I
Oh,
loved your book, but
thank
there's
you.
one thing that I just really couldn't quite get a grip on,
Okay.
and that was how birds fly in a flock and turn and fish.
Mm-hmm.
I didn't get that. Can you talk about that a little bit, please?
So flocking is really interesting, and that's not something I wrote about in this book, but something I am thinking about for the third book that I'm currently working on. So I did a piece for Wired magazine in 2014, roughly 260 years ago, about this exact thing, so collective behavior, right? So how has anyone seen like a starling murmuration or like right? How does that work? Some ornithologists, I think early 20th century, believed that they were basically telepathic, right? So that they were using some kind of, which, like I think we can laugh at, but like doesn't seem that ludicrous. Like when you see how tightly coordinated they are. The thing that really comes across from research on animal collective behavior is that those incredible dynamics are completely possible through very, very, very simple individual level behaviors. So there are the traditional models have three things. Attraction, so you must want to be near your flock mates, but also repulsion, so you don't want to be too close, and alignment. So you want to tend to move in the same direction as the birds around you. If you take those three things and just plug them into a computer model, you can create what looks exactly like a flock of birds. So this was done with a program called Boids in the mid 20th century. And it just shows that you really only need a very small number of very simple rules to create these incredible patterns. There's some Italian researchers who did work with starlings, because obviously if you study this, why wouldn't you, right? And what they showed by recording and filming a lot of flocking starlings is each starling is really only paying attention to 6 or 7 starlings around it, maybe. And it's basing what it is doing based on that. So just through that, you can have this incredible spectacle that looks like it requires some kind of top-down coordination. It doesn't at all. It's all bottom-up.
I think you did talk about this for fish in the book, right? I mean,
Yes.
so
Yes.
could it be something similar? I mean, for them, it was like the lateral line or?
The lateral line, yeah. And for vision too. I think fish use both of those senses. And I think birds are clearly using vision so it comes down to these local individual interactions with immediate neighbors, but it's probably vision that's guiding that. It's probably, I would guess, some sort of touch as well, in the same way that it works with fish. You know, the wings are very sensitive. So maybe it's a combination of air currents and vision. I don't think we really know the answer to that. Like, if you think about the kinds of experiments that you would need to really get at that, like, these are very hard things to do. You know, even just filming the birds and making sense of those videos is really hard. But like, maybe, you know, we're reaching the time when you could imagine like very, very good backpacks of the kinds that are used to trap migrating birds being used to study these intra-flock dynamics. Do like maybe two more. Okay.
Thank you so much. This
Oh.
has been absolutely brilliant.
Thank you. Congratulations on your award.
Thank you very much. What you're touching on is, you know, we're all rushing into AI and machine learning, and what you just described for a flocking bird, you know, we built this giant program. You know, this bird is flying and it's sensing and it's tweeting and it's doing all these things with a bird brain. So can you think about or think about or help us parse out how a bird's brain can process all of this information in a nanosecond? If we watched a bird fly and you think you're going to land there, no, it's not going to land there. We can't even anticipate where it's going to land. So think about how the bird brain can process that. Is it because it's been evolved for 100 and 300 million years that it's packed that much neurons into such a tight little space?
Yes. I believe so. So I think this is a really good question. And I think it actually opens up some really interesting ground, because we see animals performing these incredible feats, and we marvel at them in part because we try and imagine what it would be like if you were piloting a bird and having to deal with all that information. But of course, your brain evolved in the context of your anatomy, your physiology, your ecology, your evolutionary history. Your brain, your mind evolved to pilot a human body, not a bird one. And a bird's brain evolved in its own context. I think there's several things you can draw from this. Like, first, I mentioned this in the book, like that kind of fantasy trope of like humans turning into animals, like projecting your consciousness into another species, that these ideas are very common in our mythology, in our fiction. It just wouldn't work, right? Because your brain, the way your brain works evolved in your particular context. You can't just transfer it into another body and hope for the best. But I think it also means that we need to rethink what we define as intelligent. So we define intelligence in a human context. We are very flexible. We can use tools. We can plan and strategize. But we can't flock together in the same way that starlings can. We can't pass out the temporal fine structure of a Pacific wren's song. We can't do any of that. You can sort of bill those things as other kinds of adaptations that aren't intelligence, but then it leads you to the question you asked, right? Like, how is a bird's brain capable of doing all that? Because we sort of have this inherent sense of a bird's brain as being like a little bit less capable than ours, but it's extraordinarily capable, just in very different ways. And I think when we think about intelligent birds, they tend to be birds that are doing the kinds of things that impress us, right? They're like corvids and like New Caledonian crows and scrub jays have their episodic memories, right? But is that really more impressive than what the zebra finches are doing? I don't know. I don't really think so.